Laboratory buildings are very energy intensive. Labs use 5 to 10 times more energy than an office building. So when we start talking about a net zero energy office building, that's tough enough. When we start talking about doing a net zero energy laboratory, it's a lot harder than doing an office. So the approach on a net zero lab is to start by making the building as efficient as possible so that the net zero component is even probable or possible. So laboratories are like office buildings in that the consumption falls into 3 major categories: lighting, heating and cooling, and then things that we plug into the walls or plug loads. So it's just the proportions a little bit different, and in each category it's higher in a laboratory. So we approached each one of those end uses and looked for ways to reduce the energy. And the lighting, to give an example, and the heating and cooling for this project, we focused on what are the passive ways to provide lighting and heating and cooling. And the passive form of lighting is daylighting. The passive form of heating and cooling is natural ventilation. And there's no better place to do both of those than in this climate in San Diego. You know, I think the context of San Diego is that it's a very mild climate. That helps us. It'd be a building that's in a harsh, cold winter and a hot, humid summer climate. They use more energy. But having said that, we still use lighting in buildings regardless of the climate. And in a laboratory building, regardless of the climate, we have to provide a lot of ventilation air. We have to move air through the building to keep it safe for the people working in the laboratories. This climate does make it easier, but still there's a lot of challenges. And really the approach has been, and a lot of the innovations in green buildings is, let's try it first in a more mild climate and see if we can make it work there. And then we'll scale it up and refine it and figure out how to make it work in a more challenging climate. So you'll find a lot of the most innovative green buildings are on the West Coast because it's a little bit easier. We're paving the way, we're trying new things, and then you'll see a lot of the things that have been worked out on the West Coast, you'll see that echoed in a lot of the other green buildings throughout the US on the East Coast and the Midwest and the like. The challenge for net zero when you want to produce your electricity with photovoltaic systems is that you only have so much space on the site. And this site is pretty much the building. There's not a parking lot on the site. There's parking underneath the building. So really the boundary or our budget was how many PV cells can we put on the roof? How much energy can we create by doing that? That's now our budget. And so we used that as the constraint, and it informed the remainder of the design. So when we were talking about the design, the starting point was, well, how much energy do we have available? Therefore, the lighting, you only get so much. How can you make the lighting work with this budget? And it's quite a different approach from a standard building where we do the design, we see where we are with the energy, and then we just go buy the energy. And then, typically we try to reduce the energy, X percent. We try to go 5 or 10 or 20% below what is normal. We already had a budget on this building that is more like half the energy consumption of what a typical laboratory would have been in the same climate. From the lighting systems perspective, we tried to set up the building to maximize the use of daylighting. And the way you do that, it's pretty straightforward. You make a narrow building so that everybody is within 20 or 30 feet of a window that is daylight. And not only do we do that, we think about the placement of the windows. We don't want to have a lot of windows on the west side of the building where the sun can produce daylight but too much heat. So we designed the building to have a long axis along the east and west, and so that we have most of the glass on the north and south of the building. Therefore, we can control the solar load and the sun. We also used high ceilings. The laboratories have very high ceilings. It gave a lot of flexibility for the labs, but also created great daylight in the space. The office space has 10-foot high ceilings and lots of glass judiciously placed so that the daylight comes in a even manner and allows us to dim the lighting down. On the heating cooling systems, we took a similar approach. On the office space where we wanted to use natural ventilation because this climate is ideal for that, we made a narrow building with operable windows. And then when the windows are open, a cross flow of gentle breeze of air moves through the building. And we're lucky that near the ocean there tends to be a gentle breeze all the time. In the laboratory spaces, you can't use the operable window strategy because of safety. You need to have the air moving through the building and then being exhausted in a very even way. So we used a variety of strategies to make the fan energy be much lower than typical, and then also the heating and cooling energy produced in a way that uses a lot less energy than typical. To give you a couple examples of how we did that, fan energy, the way you reduce fan energy is by addressing and thinking about friction in the ductwork. So if we can reduce the amount of friction, and that is make ducts that are more slippery and don't have as much resistance to the airflow, the fan doesn't have to work as hard. The fan systems in this building are half the size of what they would be in a typical design. And that is a typical design where we have a lot of bends and elbows in the ductwork, and we have coils and filters that are very small, and the air has to work very hard to get through them. We made the ducts a little bit bigger. We made them more smooth. We have bigger filters and bigger coils, so the air is moving through more gently. It's using less energy, but it's also getting filtered more effectively, dehumidifying and controlling the temperature more effectively when the air moves across the coils more slowly. One of the terms for that is low face velocity. We used a similar approach when we were thinking about pumping systems in this building. Smooth pipes, what is oftentimes called short, fat pipes, and small pumps. And the whole idea is, let's think about the passive elements of the system, that is the pipes and the ducts. Let's optimize those so that the active parts of the system, that is the pumps and the fans, are smaller and lower energy.